Good morning all. Today we are going to see temperature distribution and heat penetration studies for thermal processing of food. So, before going into that, we will just see what is the motivation for us to do the temperature distribution and heat penetration test. The goal of any thermal processing is to ensure the slowest heating point, which is nothing but a cold spot within a product container which receives adequate thermal treatment, right. So, till now what we have seen is, we have seen the basic thermal processing which are going to be applied for the food, and also we have seen one lecture on food microbiology, right. So, after doing so, the end goal is to go for a process establishment. To go for process establishment, I would require the time temperature combination. So, for such time temperature combinations, after determining the time temperature combinations, we supposed to do these two tests, which is nothing but a temperature distribution test and a heat penetration test to establish the process in industrial scale, right. So, before going into that, I would like to remind you certain things whatever we have done in earlier classes. So, if you remember, we told that either microorganism or enzymes or any nutrient, the inactivation kinetics follow first order. Right. So, if we remember, what we have written is minus dn dt. So, this is nothing but the depletion of n. So, n is for here the microorganism. If it is a enzyme or nutrient, it is a concentration which is nothing but C. So, which follows k t into n, right. So, when we do the further integral calculus, so this is n naught initial concentration to final concentration n, and which is nothing but k t 0th time to time t into dt. So, which further gives me ln of n naught upon n, so which is nothing but k t into t, right. So, remember here minus sign is there, so I have written ln n naught upon n. So, or if you want to write, you can write it same way, minus ln n upon n naught, which is equivalent to k t into t, or n upon n naught is nothing but e power minus k t into t, right. But we also learned the dt value, which is nothing but a thermal death time or decimal reduction time. So, which is nothing but time in minutes or seconds in x axis. So, in the y axis it is in the log scale. So, 1, 10, 100, 1000. So, which is nothing but in the log scale. So, we told that it follows the log linear relationship, and for one log reduction. So, what is the time? So, that is nothing but my dt, right. So, since we are using in the log scale here, it would be convenient for me to convert this ln scale into log scale. So, ln into log, so what you get is 2.303 into log of n naught upon n and k t into t. So, if you want to do it in log n naught upon n, which is nothing but k t upon 2.303 into t. So, this k can be related to dt as 1 upon dt, right. So, then we can do it 2.303 into dt. So, if you want to write dt here, so this can be written as 2.303 upon k. So, if you want to represent in terms of log n naught upon n, the same relationship goes like this. So, log n upon n naught is nothing but it is in the 10th scale. So, log 10 scale. So, it is kt into t. So, the k and dt relation is kt is nothing but 1 upon dt. Right, the dt can be found out from here, or otherwise, for example, if you write the same equation in this form of y equal to mx plus c log n minus log n naught, which is nothing but log 10 will get cancelled minus kt into t. So, it is nothing but log n, which is equivalent to log n naught. So, minus kt is nothing but 1 upon dt. So, this is t, right. So, I can get my slope if you draw a line. So, this is log n versus time. So, this is x axis. So, whatever you get here intercept as a log n naught and your slope is minus 1 upon dt. So, that way also you can find out dt. Right. So, this we have already seen. So, how to find out dt, and remember we have told it follows the first order kinetics. The rate constant k is nothing but a function of temperature here. So, whatever we are doing it here is for constant temperature. Right. For example, if you are applying any thermal processing, my temperature has to rise from the initial product temperature to the processing temperature. So, in that case I will have temperature variation depends upon the time, right. So, in that case I would require such dt values at different temperatures. So, that is where the concept of z value came. So, the z value is nothing but same concept, but in z x axis. So, you have a temperature which is in degree centigrade. So, in y axis you have log dt values. So, the same linear log linear relationship. So, the slope is nothing but minus 1 upon z, right. So, from this I can find out my z value, which is which will be in degree centigrade. In the previous graph, so what you get here is dt, which is in time unit, either minute or second. Okay. So, I will collect certain dt values at different temperatures, then I will plot temperature versus log dt. So, the slope is nothing but minus 1 upon z. So, from there I can calculate z value. The another important value is nothing but f value. So, by which only I am going for, this is a equivalent process value. So, with which only I am going for the process establishment, right. So, this f value is when you refer. So, it is nothing but f of t reference and z, right. What is my t reference temperature and what is my z value. So, which is equivalent to 0 to t lethality rate into dt. So, what is this lethality rate? So, this lethality rate is nothing but 10 to the power of t minus t reference upon z, right. So, z is the reference z value, this is reference temperature. So, this is the temperature. Most of the time it is a function of time, the temperature is a function of time, that is why you are integrating to 0 to t. So, then your f value, which is nothing but f of t reference at z is equivalent to 0 to t 10 to the power of t minus t reference upon z into dt, right. So, this is my f value. So, here remember there are certain process which are constant temperature process. So, by now we know the sterilization process, right, or pasteurization. So, we were talking about in the earlier lectures the holding, right. So, heating up to the particular temperature and holding it for certain time, right. So, for example, in the pasteurization, if you see 63 degree centigrade for 30 minutes, so it means that first from initial product temperature to 63 degree it is getting heated and it is holded for 30 minutes. So, in that case it is a constant temperature holding. So, if my temperature is constant here, then there is no need. So, what I would be doing in that cases, it is nothing but 10 to the power of t minus t reference upon z. So, 0 to t dt, so which is nothing but t into 10 to the power of t minus t reference upon z, right. So, this is the way I calculate the F value. So, if my reference temperature is nothing but 121 degree centigrade, or if Z value is 10 degree, so which is mostly applicable for Clostridium botulinum. So, then my F value is called F naught value. So, this also, and one more thing is, we are talking about here about the microorganism. So, if I talk about in terms of nutrient quality, that I call it as a C value. So, here I told lethality rate is nothing but 10 to the power of t minus t reference upon z, but if my cooking value, if I need to find out for the nutrient, it is nothing but 0 to t 10 to the power of t minus t reference. Remember, this is the temperature of the product where you wanted to calculate the nutrient deactivation or nutrient deterioration. So, this is nothing but ZC. So, the corresponding Z is for vitamin or any nutrient, right. So, that is ZC, right. And also this F can also be related with your D value, which is nothing but D reference into log of N upon N naught. N naught is nothing but initial microbial concentration and N is nothing but the final microbial load, right. So, these are all the basics before going to temperature distribution or heat penetration test I should be knowing, right. So, what are all those? The DT value, thermal death time value, and the Z value, so which is a function of temperature. So, then my F value, right. So, now we will go back and check here. So, the goal in thermal processing is to ensure that the slowest heating point within a product container receives adequate thermal processing. So, the moment I say, for example, any pasteurization or pasteurization which goes by conventionally 6D process or sterilization which goes by 12D process. So, for that example we have just seen, right, 63 degree 30 minute means. So, my cold spot or the slowest heating point should receive 63 degree for about 30 minutes. So, that is what the goal of the thermal processing is. So, for in container sterilization process, there are two stages of thermal process establishment. In container in the sense batch. So, one is the temperature distribution test. So, that is what we are going to discuss in the whole class, and to identify the slowest heating zone. The second one is the heat penetration test to determine the temperature history of the cold spot in the pre-packaged food, for example, canning or retarting, right. The pre-packaged food is in the cans. So, what we are doing is retarting. But why we specified especially in container sterilization? For the inline sterilization you may not require the temperature distribution test, because it is directly the heat is given to the product. So, you would like to have their heat penetration test only. So, this may not be required, but it is a in addition to the heat penetration you would like to have, but that is not necessary. So, the temperature distribution test is nothing but to see which is the coldest point in the container itself, or whether my container receives the process temperature uniformly, right. So, that is what we wanted to do, temperature distribution test. So, my container everywhere the temperature is distributed uniformly or not. So, that is what we are meant by temperature distribution test. The first step in conducting the test is the selection of test retard. First we need to select the retard with test retard, then the survey of the processing room should be done to select the test retard. So, where I am going to keep my retard. The survey include the examination of the following factors. One is if we are applying a steam, the steam quality, temperature, etc. Then the air, because we have already learned that. So, to have the pressure balance between inside the can and outside, so we also use compressed air. Then water supplied to the retort for the cooling period, and the type of retort and size of the each retort in the retort room. There are certain sterilizers, one of the we would be seeing that hydrostatic sterilizer. So, that operates based on the hydrostatic pressure. So, to need to have hydrostatic pressure, so I need to operate that particular sterilizer in the certain height. So, that may not be, the sterilizer may not fit into that particular room, the processing room. So, in such case, so where should I keep? So, in that case, the size of the each retort also comes into play when I do the survey. And purging and drainaging, whether proper system is employed, and retort loading conditions, the container information, which type of product we are going to heat, and maximum number of containers in the retort. So, this also we have seen. So, there are certain regulations are being employed, the container size as well as the retort size. So, based on the size of the container, we can fix the number of containers in the each retort. There are standard size which is nothing but a good manufacturing practices, you may would like to refer for that. So, to conduct the DD test, the situation resulting in worst case conditions for commercial operation should be selected. So, this worst case condition is nothing but whenever I select the F value is nothing but from here, right, from which I will calculate the F value. So, this F value we go for safer F value. For example, if my F value is nothing but 2.4 minute, right. So, which is for 12D reduction of Clostridium botulinum. So, I would like to go for 4 times or 5 times of that, right. So, that means I am ensuring my process is safer, right. So, for such cases I would like to create a worst case condition in the sense, for example, one example we can see. So, we can create this by using the initial temperature of the product. So, though my initial temperature of the product is at atmospheric condition for say 30 degrees centigrade. So, I would like to start this with 25 degrees centigrade. So, I will take 5 degree less than the actual temperature of the product, so that the heat treatment what I am employing ensuring the 5 degree. For example, instead of 30 degree, if I am able to heat from the 25 degree, so I am applying extra heat, right, for the particular thermal processing. So, this is nothing but one example for worst case condition, right. So, that I am keeping my thermal process safe to kill all the microorganisms in that particular thermal processing, right. So, in that way I create worst case conditions, and containers may be filled with water for convection heating products while doing test. If it is a convection heating product, so instead of liquid food products I would use water. If it is a conduction heating process, most of the time the direct food product itself would be used, or starch solution, so which gives me the very thick solution, right. So, that also can be used during the conduction heating product. And temperature measuring devices in sufficient quantity should be used to monitor the temperature of the heating medium within the retort. So, why we are doing this temperature distribution test? When my steam is on inside the retort, so whether the steam, the heating medium or steam what I am using would be able to heat the retort uniformly, right. So, for that I need to employ temperature measuring devices in sufficient quantity, so that each and every, almost all the places I am checking my temperature whether it is equivalent to the heating medium temperature. The most common TMDs are temperature measuring devices are duplex type thermocouple, which is nothing but copper Constantine with the Teflon insulation. And also, if you remember the earlier classes, so we also told, right. So, the retort will have flow meters, then temperature detectors, then pressure, then for steam the bleeders, vents, etc. Right. So, I also need to ensure the pressure indicating devices should be used to monitor the pressure in the retort shell, and also the flow meters should be used to measure the flow rate of the process water during come up and heating time, and also test should be conducted at the maximum retard temperature used during the process, right. So, while doing the test, then we need to ensure it is a maximum retard temperature for say 121 degree, right. So, these are also to be ensured while doing the temperature distribution test, and the critical parameters which should be recorded during temperature distribution test includes the temperature controller set point. So, this is the processing temperature set point, and another one is initial temperature of the product, then the time when steam is turned on the heating medium, and the temperature of the heating medium when I am turning on the heating medium, and flow rate of the heating medium, time when the reference TMD achieves the process set point. For example, my initial product temperature is at 30, so I am switching on the steam at 121 degree centigrade. So, then I also need to record the time when the reference TMD achieves the process set point, which is nothing but 121 degree centigrade. And also this is the come up time, which we call it as a cut, is the time required by the retard to attain a minimum required process temperature with the uniform distribution in the retard. So, if I want to fix the retard temperature as a 121 degree centigrade, so from switching on the heating medium to evenly distribute the retard to 121 degree centigrade, what is the time taken, which is nothing but the come up time. So, these all critical parameters should be recorded during TD test. So, the second one is heat penetration test. As we said earlier, the temperature distribution test is done in the retard or in the container to ensure the temperature is uniformly distributed in the container. This heat penetration test is done on the product side, whether the coldest point of the product is achieved the thermal processing temperature or not, right. So, to determine the heating and cooling behavior, not only heating, then after the thermal processing we also cool the product to the normal atmospheric temperature. So, that also taken to account. So, to determine the heating and cooling behavior of a specific product package combination in a specific retard system for establishment of a safe thermal processing. So, our aim is to make even cold spot to achieve the correct thermal processing temperature. The HP study is conducted before starting production of a new product using a new process. So, mostly the test is conducted when we start the new product in the new process, and also there is a guideline 6 months once you need to also test it, and whenever you change something, for example valve or pumps, if such cases are changed, then also you need to do these TD as well as the HP test in the in container thermal processing. If it is a inline thermal processing, then you can go for the heat penetration test. The test involves locating the cold spot in the food within the package and establishing the scheduled time and temperature. The conduction heating product in a cylindrical can, the cold spot is the geometric center of the can. So, this I think probably we have discussed already also. So, this is my can. So, if it is a solid food particle, then my geometric center of the can would be the coldest point, because what we are employing the heat is at the wall. So, when it penetrates, so based on the thermal conductivity of the solid particle. So, the coldest point lies in the geometric center of the container. If it is a convection heating in the cylindrical can, the cold spot is between the geometric center and the base of the container. So, in between somewhere. So, mostly they say 1/10th of the height of the container. And also, for example, if I have a solid particle in the liquid, then it may be between the bottom. So, this height to the geometric center of the container. So, in between somewhere it lies. So, in heat penetration test, a study should be conducted to determine the location of the cold spot for a specific product package process combination. So, this is like if I know the cylindrical can and if I know the products are fully solid particles, then I can come up saying the geometric center would be the cold spot. But however, so we need to insert the thermocouple and we also ensure that is the cold spot of the product package process combination. And the cold spot is usually determined by conducting series of HP tests employing several containers with the thermocouples inserted at different locations. So, it is not like one container I will just keep and thermocouples I will place it at 10 different places and conduct the HP test. It should be done at several containers and also several thermocouples inserted at different locations. The design of a HP test should consider all the critical factors to deliver adequate thermal treatment to the slowest heating point within the product. So, it also has to taken into account all critical factors what we have seen for temperature distribution test. So, we are going to see what are all the critical factors, and a HP test should include at least 10 working thermocouples from each test run, and HP test should also be replicated to account for product, package and process. So, we need to repeat it most of the times 2 replications would be done. If any of the 2 replications are quite different, then we may go for third one as well. So, the essence is we need to do it for a number of containers and we need to do it with number of thermocouples inserted at different places, and the replication also should be done based on the product, package as well as the process. So, in terms of containers, what are all the critical factors? So, one is type, metal cans, glass jars or pouches or semi-rigid containers, which one. The second one is size and dimension of the container, then whether the vacuum is created inside the container or not, and the head space involved, and container orientation, whether we are keeping it vertical or horizontal, then fill method used during the packaging, then symmetry of rotation, whether end to end in the sense, so you do it like this. So, the axial rotation is also there. So, it is in this way, right. So, the symmetry of rotation also to be taken into account. And the second one is the product also, the product formulations, the product fill weight and the viscosity of the product, and the solid components present in the product, and preparation method, how did we prepare the product, and any rehydration is there when I am processing the dried components, and heating mode, whether it is a conduction, convection or which mode I am using, and pH of the product and water activity of the product, density. So, all are critical factors when we do the heat penetration test, because it obviously affects my temperature distribution from the wall of the container to the food product. Then the filling and sealing factors, fill temperature, seal integrity and retard factors, and type of heating medium used, whether it is a steam, air or steam air combination or water immersion or water spray technique, which type of heating medium I am using. Then the come up time, so how long does it take to reach the exact heating medium temperature. Then racking dividing system in the sense I have a retort and here I have a crate. So, in this my containers are stacked. So, this also the gap between the 2 containers when I insert the thermocouple. So, everything have to be taken into account while doing heat penetration test. Once the cold spot and all critical factors are determined, 2 full replications of each test to be conducted. This is what I told. Once I determine what is my cold spot and other critical factors, then I need to do at least 2 replications. So, if both are a bit different, then I may go for third one as well. And so, how are we going to put it in a curve, right, the heat penetration curve. So, the heat penetration data are evaluated by plotting a heat penetration curve. So, the data are plotted in such a way that there is a linear relationship between the product temperature and the heating time. So, right, for example, if I am telling the 63 degrees centigrade for 30 minutes. So, first I need to heat my product temperature to 30 to 63 degrees centigrade. So, this involves the time temperature combination, right. So, then after that I will hold it for 63 degree for 30 minutes, right. So, this talks about how my product temperature varies with the heating time. And then a plot of log Tr minus Tp, Tr is nothing but a retard temperature and Tp is nothing but a product temperature versus time, known as the temperature deficit plot. So, is linear where Tr is the retard temperature. First I would be doing heating time versus Tp, then log of Tr minus Tp versus time, which is nothing but a temperature deficit plot. Heat penetration curves which are linear throughout the heating time are referred to as a simple heating curves, right. So, if you are following only one particular mode of heat transfer, but if there are any changes between the conduction to convection, for example, I have a container in which my liquid and the solid particle are there. First my the heat whatever I employed through the retort has to conduct through the walls, and from walls to this liquid medium it is a convection. So, this convection heat current then see the solid wall of the particle, which is a solid particle, then there is a conduction happens, then from the wall of the solid food particle it has to penetrate through the inside. So, there is a convection to conduction changeover is there. So, in such cases what you would get is broken heating curve. A heat penetration curve for a broken heating profile has two linear portions due to change in the heating mode from conduction to convection or vice versa. The heat penetration data can also be plotted as an inverted scale plot with Tp. So, we will just see. So, how my heat penetration curve look like. So, this is my time. So, this is log of Tr, which is retort temperature, minus Tp, this is nothing but a product temperature. So, this must be 1, 10, 100, I am not drawing into scale, I am just doing it. So, this is the way my heating curve looks like. And also we told, for example, I can plot it directly with the Tp also, which is nothing but a product temperature, which is in degree centigrade, which is also in degree centigrade. If I had to do that, this is nothing but Tr minus Tp equal to 1, when Tp is nothing but Tr minus 1, maybe this is Tr minus 10. So, this is Tr minus 100 and this is Tr minus 1000, right, which includes the come up time. So, here because of this come up time you will not get straight linear curve. So, I will extend this to straight linear curve. So, this point I will call it as a log of Tr minus Tp IH. So, which is nothing but pseudo initial temperature, pseudo initial product temperature. Right. And also there is a factor called FH, right. So, how it is being determined is, so it is nothing but 1 log reduction, for example 100 to 10. So, this is nothing but the slope, which is nothing but FH. So, if you see from the mathematical point of view, so I can write y equal to mx plus c. So, y is nothing but here log of Tr minus Tp, right. So, and my x is nothing but t here, and my slope is nothing but minus 1 upon Fh. So, m into x plus c, c is nothing but the intercept here. So, which is nothing but log of Tr minus Tp IH, right. So, from this I can also introduce another factor, which is nothing but a JH. JH is nothing but Tr minus TIH upon Tr minus, so this is Tp, right. So, this is Tr minus Ti, which is nothing but a initial product temperature, because just to tell initial product temperature. So, the pseudo initial product temperature is determined using just extrapolating the heating curve. So, from this I can calculate this one. So, which is nothing but Tr minus Tp IH is nothing but JH into Tr minus Ti. So, if you substitute here, so this becomes log of Tr minus Tp which is equivalent to minus T upon Fh plus log of Jh into Tr minus Ti, right. So, this factor we call it as a G, right, and if my T equal to B at the end of the process, at the end of thermal process, then my B is nothing but, so Fh into, so this goes here, this comes there, so it becomes minus. So, then I can write log of Jh into Tr minus Ti upon G into Fh. So, this is nothing but total process time, right. So, this formula is called Ball's formula. Right. So, from the heat penetration curve, which is plotted as time versus log of Tr minus Tp. So, I can calculate two factors, one is Fh and Jh. So, from this I am calculating the process timing at the end of any thermal process, which uses Fh into log of Jh Tr minus Ti. Tr is nothing but retard temperature, I is nothing but your initial product temperature, and Jh comes from the heat penetration curve. If I know G, then I will be able to calculate what is the time required at the end of the thermal process. And also you have to calculate the equivalent F value for thermal process establishment, that can be done using F of reference into at Z, which is nothing but 0 to T 10 to the power of T minus T reference upon Z into dt, which is nothing but minus d reference log of n upon n naught. Okay. So, this we have discussed, this is what I just explained you. So, a plot of log of Tr minus Tp versus time, so that we have drawn, and from that we also told about the simple heating curve what we have drawn, and broken heating curve if there is any change in conduction to convection, and inverted scale plot with Tp also I have shown you here using the Tr, right. So, this is Tp versus time. So, heat penetration test, there are two important parameters that define the simple heat penetration curve. One is the negative inverse of the slope known as heat rate factor. So, whatever we have shown as a Fh, which is nothing but a heating rate factor, which is defined as the time required for the heat penetration curve to traverse one log cycle, right. So, here you might have seen the one log cycle. So, what is the time taken, which is nothing but a Fh, and a lower Fh value indicates the faster heating time. So, that is obvious, because if you get the time less, then that means you are getting a faster heating, right. The subscript H indicates the F value is for heating process. So, similarly you can find out Fc as well, which is nothing but for cooling process, because any thermal process, after the thermal processing is done, then you are supposed to cool the product to the atmospheric temperature. The second factor what we have seen is nothing but the intercept of the heat penetration curve. The intercept is obtained by linear extrapolation of the curve back to 0 time. So, the intercept is nothing but Tr minus TIH, where TIH is pseudo initial product temperature. I might have shown you as TPIH, which is, I have also included the P term, which is nothing but pseudo initial product temperature determined by linearizing the entire heat penetration curve, right. So, this we have seen. And this method involves graphical or numerical integration when the temperature distribution is known either from the heat penetration data or heat transfer equations. So, this can be done in two ways. One is either you get by graphically, or you can do also numerical integration, because you have seen here, right. So, F reference at Z is 0 to T 10 to the power of T minus T reference upon Z into dt. So, this T is nothing but a function of time. This can be done either directly from the heat transfer equations, or you can insert the thermocouple and get the product time temperature history. The time temperature graph is converted into lethal rate versus time graph. So, the area under the curve is nothing but the F value of the process. So, once I do heat penetration test and I come up with the T as a function of time, temperature as the function of time, then I will be able to calculate lethality rate, which is nothing but 10 to the power of T minus T reference upon Z, right. So, from this I will be able to calculate F as a 0 to T my LR into dt. So, this integration can be performed using numerical integration, either Simpson rule or trapezoidal rule, or you can simply plot time versus LR. So, your curve something look like this. So, then if you calculate the area under the curve, so that is nothing but your F value. So, this way also one can do. Anyway, we will do the problem, one particular problem in the subsequent class to make you understand this, how to calculate the F value. So, there is a devoted lecture for that F value determination, there we are going to see. Here we are going to see only theory behind it, how to do temperature distribution test to ensure my retard temperature is uniformly distributed throughout the retard, and the heat penetration test where your cold point of the food particle receives the temperature which confirms the killing of microorganisms or lethality. That is what it is told. So, it can be done in any numerical method also, this integration, or you can directly draw LR versus time and find out the area under the curve. The thermal process developed by the general method is depend on product package process parameters used in the test, remember. So, this is what the general method. So, here I am not using any the formula. So, here I can directly get the temperature as a function of time, then using that I will calculate lethality rate, then I use the any numerical integration technique or simple graph to find out the area under the curve and find out F value. The thermal process is established only for the actual conditions tested, because I am just doing it for particular retard temperature and initial temperature. Therefore, this general method is not useful to determine the F value for different retard temperatures and initial temperature of the product. So, thus the general method does not allow the assessment of the process deviations, right. So, the heat penetration test can be done in three ways, right. One is general method, the second one is formula method, what we have seen, right. So, how do I relate my B with the parameters what I am getting from the heat penetration curves. So, the third one is numerical method. The first what we are discussing here is a general method. In the general method, so I will just get the temperature as a function of time, then from there I will calculate the lethality rate, from there I will calculate F. So, this is the restriction here is, or limitation here in this general method is, I am using the actual condition. So, which is nothing but the retard temperature and initial temperature is fixed. So, if I want to calculate, if I want to change for example timing, so I am getting the temperature versus time plot for 2 minutes once. If I want to calculate what happens at 1 minute 1, I cannot change, because whatever the conditions I have given is for fixed condition. The general method relies on time temperature history at the cold point. So, thus it can be used for both in container as well as in flow sterilization. So, you can use it for both the thermal processing, whether it is a batch or continuous. For a fluid product in a flow sterilization process, the process time for given F value and process temperature can be calculated. The required process time must be achieved for the fastest moving portion of the fluid particle. So, this is very much important. This also we will study in the validation of the thermal processing. Here what they would like to mention is, for example, in the pipe if my fluid particle is going, so it follows always the parabolic velocity distribution for laminar flow. So, the product here at the center of the pipe is the one which comes out at the earliest. So, that means, so these particles here in this region stays more compared to this particular particle which is in the center, right. So, based on this particle only, the time temperature combination whatever we design to be done for the process establishment. For example, the length of the holding tube is nothing but U max into T. T is nothing but whatever the time temperature combination, that time here it is. So, this U max is nothing but 2 into average velocity if you consider in the laminar flow is nothing but you consider the fluid as a sheets, and the same U max is nothing but 1.2 into u bar is here is average velocity. If you are taking turbulent flow is nothing but where your eddies are forming. And also there is another discrimination here, whether it is a Newtonian fluid or non-Newtonian fluid. Newtonian fluid in the sense which follows the Newtonian's law of viscosity. So, that means your viscosity and shear rate follows the linear relationship, and non-Newtonian fluids are most of the foods are non-Newtonian. Newtonian example is nothing but a water. Non-Newtonian you can consider any juice or for example the thick soups. So, those follows as a non-Newtonian. So, if it is a non-Newtonian, then again your U max will be something as the function of n as well as u. So, n is nothing but a flow behavior index. So, like this the length of the holding tube which has the U max. So, this U max depends upon many factors. So, these are also to be taken into account when you do the heat penetration test. So, the formula method, the ball introduced that I already have derived here. So, the B from the heat penetration test. General method, just to take T as a function of time and substitute in the lethality rate, from there it calculates the F value. But here in the formula method, ball derived a formula just to avoid this process because it has a limitation, I cannot apply generally. So, that is what he came up with the formula method. So, in the formula method what happens is to overcome the limitation of the general method. So, Ball, he is a scientist. So, related the value of G is nothing but log of Tr minus Tp, at the end of the process is nothing but G. So, he came up with the G to the dimensionless ratio. So, he introduced Fh upon F of Tr. So, Tr is the retard temperature for various Z values and cooling lag factor Jc. If F value at Tr is u, then the equation for dt curve is done. So, that means what he did is, so log of u, so instead of G what we have seen over there, so he introduced, so log of F250 Z minus Tr minus 250 upon Z. Okay. So, he introduced the factor u here instead of G. Then Ball defined the reference TD curve. So, when he defined this particular equation, so this equation and the formula what we have used earlier both have same slope, right. So, he came up with the reference TDT curve. So, for that he used this particular equation and he taken that F as a 1, F250 as a 1. So, then this equation becomes log of Fi, which is equivalent to minus Tr minus 250 reference temperature upon Z, right. Fi, which is a function of Z value, and Tr can be found in the literature. So, this literature I have given you. So, this Ball, after he defined the Stumbo in 1973, so he has introduced the Fi as a function of Z and Tr. So, then he defined here log Fi. So, from this u can be calculated. How? So, the log Fi is given here as a this one. So, log u is nothing but log of F250 Z minus log Fi, right. So, minus of minus plus. So, if I do it, so this is u into Fi F250 Z. So, from this u can be calculated, right. Thus, u can be calculated if the value of F250 is known, right. So, if I know F250 at various Z values, then u can be calculated. Once u is determined, the G value, G, right, what he did, the G is replaced by u value. So, then if I know u value, then G value can be determined from Fh upon u and G correlations, right. So, he calculates Fh upon u and G already know. From this correlations I will be able to find out my G value. Once G is determined, then we can calculate B using the same formula. Okay. So, the calculated process time is applicable to processes where product comes in contact with the steam at retard temperature without any lag. So, this is calculated without any cut. So, if you want to account for your come up time, then your process time is nothing but B minus 0.42 of cut. 42% of the contribution to be given to the total processing time. So, in batch retards there is a time lag in getting the retard temperature. So, that is nothing but 42% ball method contributes, and also he has taken the JCS 1.41 and also the another assumption is FCFH. So, these were relaxed when the Stumbo, and one more reference I have given here, one is this Stumbo and another one is Hayakawa. So, they both worked on it and they removed the removed or relaxed these assumptions made by the ball, and they accounted how to increase the accuracy of the formula method. And the ball method often underestimates the F value for conduction heating products, and for products packed in thin pouches, the ball method can overestimate the F value as the JC value is substantially less than the assumed value of 1.41. 1.41 the assumption. So, because of that it overestimates the F value. The major limitation of the ball method is in its ability to handle the variable process temperature. So, we cannot handle the variable process temperature. Apart from that, there are numerical methods. One is nothing but numerical. So, what it does is it uses the finite difference method to calculate the heat penetration curve. So, it does both the things, one is analyze and another one is calculate. So, analyze in the sense it calculates the using FDM approach, it calculates the heat penetration test and get the parameters from over there and calculate the F value for the process establishment. There are other numerical packages as well. So, I would like to request you to check few reference book given in this lecture. So, you will get to know what are all other methods. So, in short, so we have done how to do temperature distribution test and heat penetration test and what are all the methods available. So, in the subsequent classes we will be doing some of the problems, there you get clear how to calculate. So, these are all your references and additional resources whatever I used in this lecture. Thank you.